For the second part of the lecture, I'm going to continue. So you've already seen in the past couple of problems that we can calculate pressure or use pressure to calculate things like force. Well, now, oh, what just happened? I apologize. Now we can actually use pressure to help us derive another formula. And we know that pressure is equal to the force over the area. Well, remember that force oftentimes is simply equal to weight, and weight can be found by multiplying mass times gravity. Through a series of substitutions, so we can substitute mass, we can substitute volume, etc., we end up with the following formula. And remember, you don't have to understand how this formula is derived. I just wanted to include it here in case you were interested. So we now see that pressure also equals the height. So H is height. Rho is density. And G again is gravity. And y'all actually used this formula on the previous page, but I wanted to show you how that was obtained and how we can actually relate this back to force divided by area. So we're going to apply this again. We're going to calculate the depth below the surface of water at which the pressure due to the weight of the water equals 1 atmosphere. And we generally say when somebody is at sea level that the atmospheric pressure is about 1. All right, so we have this value here for pressure. And I'm going to give y'all additional information because if you noticed, the units we've used in the past couple of problems for pressure were pascals. Pascals. And I want to make sure that y'all have the proper units because we can't use atmospheres here, but I will get to that momentarily. We also know the value for the density of water. We're working with water, so we know this is just 1 times 10 to the third, and that's kilograms meters cubed per meter cubed. And if we know we're calculating the depth or the height, you could also say, then we're going to be using P equals H times density times gravity. If we have density, we always know the value for gravity, and we have the pressure, we can solve for height. And I'm just going to rearrange this so we can do that easily. P divided by, and this is rho times G. You might remember this part from the reading, but if you don't, that's okay. 1 atmosphere is also equal to 1.01 times 10 to the 5th newtons per meter squared. And that also equals, I'll just write it up here, 101 kPa, so kilopascals. So then a Newton / meter squared would just be a Pascal. Okay, we are ready to plug in. So we have our pressure now, which is 1.01 times 10 to the 5th, and that's newtons per meter squared, which is also pascals. Density is 1 times 10 to the 3rd kilogram per meter cubed, and gravity is 9.8 meters per second squared. We solve this, and we find this height or this depth to be approximately 10.3 meters. So we can go around 10.3 meters below the surface of water, and at that point, the weight of the water would equal about 1 atmosphere. And you would definitely feel that if you've ever swam down even to the bottom of an 8-foot swimming pool, you can feel the pressure change in your ears. Okay. take a look at the next one. This is, well, Pascal's principle lets us discuss how changes in pressure affect a fluid in an enclosed space. So this principle tells us that a change in pressure, which is applied to an enclosed fluid, meaning one contained in something, a valve, a pipe, just a regular container, any change in pressure that's applied to that fluid will be transmitted undiminished to all portions of the fluid and to the walls of the container. So that pressure will be applied to all parts of that fluid and of the container. And we're going to go ahead and do a calculation using this. And this one's a little bit harder to understand, but y'all have got this. So we're going to consider this hydraulic system shown over here on the right. It says a force of 100 newtons is applied to the brake pedal, which then acts on the pedal cylinder, and we call that the master, through a lever. A force of 500 newtons is exerted on the pedal cylinder. Don't worry about this part. If you want to go do that, you can. Otherwise, it is completely unnecessary. Pressure created in the pedal cylinder is then transmitted to the four wheel cylinders, and we know that's going to be undiminished because this is a closed system. The pedal cylinder has a diameter of 0.5 centimeters, and each wheel cylinder has a diameter of 2.5 centimeters. So calculate the force created at each wheel cylinder. So because, let me just write this here. Because of Pascal's principle, we know that P1 is equal to P2, meaning the pressure that is exerted to part 1 will be exerted to part 2. So it's going to be exerted undiminished to all parts of this system. So then we would consider, in this case, the 1 to be the first part the pressure is applied to, which is the pedal cylinder. And then the 2 is going to be whatever the pedal cylinder attaches to, which in our case, those are the wheel cylinders. Since I'm looking for force, I'm going to need to substitute in the formula for pressure. So we know that pressure is equal to F over A. So I'm just going to go ahead and replace these. So we're going to have F1 over A1 equals F2 over A2. I'm going to rearrange this equation so that we have F2 equals, and that would be F1 times A2 over A1 equals F2. I'm going to go write the F2 on the other side. And this equals that. Now we need to go ahead and find our areas for each part. So remember, A2 is the area of the wheel cylinder, and A1 is going to be the area of the pedal cylinder. So let's check out the information we have for this. I see I'm going to do this in blue. The diameter of the pedal cylinder is 0.5 centimeters, which would be 0.00500 meters. And here it would be 0.0250 meters. And that's for the wheel cylinders. Well, because they're cylinders, we know that cross-sectional area is going to be a circle. So we would have that the area for a circle, remember, that equals pi r squared. So let's start plugging in everything we know. The only thing we need to make sure we get right is this first force. And I'm seeing the numbers 100 newtons and 500 newtons. But remember, part 1 is referring to the pedal cylinder, so we want this 500 newton force because that's what's actually exerted on the pedal cylinder. So that's 500 newtons. And I'm just going to do the area here. So pi and then R squared. So A2 is the wheel cylinder. And the wheel cylinder had a diameter of, so that's times 0.0250. That's meters, and that's squared because that's pi r squared, and that's divided by. Then we have A1, which is the pedal cylinder, and that's going to be pi times, and then r squared again, so 0.00500 meters squared. Pi cancels out, and when you do this math here, you should find that that pressure is about 1.25 times 10 to the 4th newtons. Okay. Let's go to the next problem. And I'm also going to note that this was the end of chapter 11. So the next part is going to be part of chapter 12. One of the first things I like to talk about, and let me just ignore this and ignore this. It's confusing. One of the first things I find important to mention before I actually start working problems with y'all is that, hold on, this starts 12.1 and 12.5. Are the concepts of flow rate and velocity when it comes to fluids. Remember, fluids can be either liquids or gases or plasmas, just not solids. Flow rate and velocity are going to be related, and I think it's pretty obvious here which variable represents velocity. It's this one. So I'm betting y'all can guess that Q is flow rate, even if you didn't read this, which I hope you have. So we can figure out how quickly the fluid is flowing through some kind of pipe or system. That could be a river, could be an enclosed space where a gas is traveling from one section of a chemical plant to another. There's a lot of examples. So generally, the greater the velocity of a fluid, we're going to use water in this example. So the greater the velocity of the water, the greater the flow rate of the river. But remember, flow rate is also going to depend on the size of the area that water or fluid is flowing through. So that's why we have this term here for area. We always have to know the area of the section the fluid is trying to flow through. Let's go ahead and apply this by figuring out how many cubic meters of blood the heart pumps in a 75-year lifetime. And we're assuming the average flow rate is 5 liters per minute. Okay. So we want to know some information about cubic meters of blood. Cubic meters, so that's meters cubed, and it's blood. Well, that's a unit for volume. So it wants us to find the volume, or they're giving us information about the lifetime of this individual and then a rate in liters per minute. I can already see an issue here because I'm given a lifetime in years. However, I am given a flow rate in liters per minute, and that's not going to work out when I think about my units. So we know that Q equals AV, and that V stands for velocity. So if we're looking for volume, how on earth are we supposed to get that in there? Well, I don't think I actually showed y'all this part. There's another way we can look at flow rate. So we can also say Q equals V over T, and this time, this is a capital V, and velocity is lowercase. V stands for volume, and T stands for time. And I'm sorry I didn't show you all that. So if we consider the information we've been given and the information we want, we're definitely going to have to use this second equation. So let's go ahead and figure out, let's see, I don't really want to convert the flow rate into liters per year. Instead, I'm just going to convert 75 years into minutes so that I have matching units of time. So 75 years. All right, let's start. What do we know? We know 1 year is 365 days. And we know that 1 day is 24 hours. We know 1 hour is 60 minutes. And when you add this all up, or not add, I'm sorry, multiply it all together, you would get about 3.94 times 10 to the 7th minutes. I don't really like seeing lifetimes thought of like this. Just reminds you of how short life is. Sorry, that was a weird tangent. So I have minutes, and I know that my Q value is 5 liters per 1 minute. So now I have T and I have Q. All I need to do is solve for V. Well, let me rearrange this to be V equals Q times T. Okay, so that's going to be 5 liters per 1 minute. Times, and then T is 3.94 times 10 to the 7th minutes. And when you do this math, we can put that over 1 if you want. 1.97 times 10 to the 8th liters is what the volume equals. So this is V. But wait, we're not done. This has asked for the volume in cubic meters. Well, we're going to have to get liters somehow to cubic meters. So let me remind y'all of a couple of things. Number one, 1 milliliter is approximately equal to 1 centimeter cubed, which means 1,000 liters would be equal to 1 meter cubed. So now all we have to do is convert, and I'll do this in blue. So 1.97 times 10 to the 8th liters. I'm not going to write anything here. I'm going to put 1,000 liters, 1 meter cubed equals. So we're just dividing by 1,000, and that would be 1.97 times 10 to the 5th meters cubed. So this is how much blood that a heart would pump in a 75-year lifetime, or an average heart. We're going to do another one, which relates back to healthcare. And this time we have the aorta, which is the principal blood vessel through which blood leaves the heart to circulate around the body. We're going to calculate the average speed of the blood if the flow rate is 5 liters per minute. So we have the same flow rate, and we're told that the aorta has a radius of 10 millimeters. Okay, 10 millimeters. Let's go ahead and convert that to meters. We know we can't ever have millimeters or centimeters or nanometers or anything like that. So that would be 0.101 meters. 0.010 meters. That's R. We already know our flow rate is 5 liters per minute. And what else do we know? Well, we know that if we're looking for average speed, that means we're looking for this. And we have an equation that lets us find that. So we just need the area. Okay, let's think about a blood vessel. Well, the cross-sectional area, again, it's going to be a circle. So the area is just pi r squared, which we can calculate really fast. And that would be 3.14, 3.14 times 10 to the negative fourth meters squared. Cool, so let's solve for velocity. V is Q over A. Let's see if we're going to run into any issues here. I believe I am seeing an issue. We have meters squared and we have liters per minute, and that is not going to work because we know velocity should be in meters per second. So that doesn't change. It's the same as it has always been. We're going to have to do some unit conversions. So let's go ahead and do that. We can leave meters squared alone, so our A value is perfectly fine. But let's go ahead and convert this liters per minute. That's going to be 5 liters per 1 minute. If I need meters per second, let me go ahead and get that 1 minute is 60 seconds. That allowed me to cancel out minutes. Now I need to get from liters to meters. And the only way we had to do that was by the information given to you in the previous problem, which was this. And then that lets us cancel out liters. So this would be 5 divided by 60, and then divided again by 1,000. And that would give you 8.33 times 10 to the negative fifth meters cubed per second. Okay, well, this should work out. So we have 8.33 times 10 to the negative fifth meters cubed per second over 3.14 times 10 to the negative fourth meters squared. And this does, in fact, give us 0.265 meters per second. If you're not sure how that happened, remember when you divide a fraction, it would look like this. So I'm going to write out the units that are involved. S, and we're dividing that by m squared over 1. So then that would end up being m cubed over m squared s. So all of these cancel, that cancels, and we're left with meters per second. And that's how you end up with this unit. All right, that is it. So you've seen part of chapter 11 and part of the calculations you can do in chapter 12 as well. And I hope y'all are already finding this significantly easier than the modules in the last unit. Let me know if you have any questions.